Hello. Yes, so my name is Alexander Eckert and I want to give that overview over the sensor-based sorting technology. I was working in that field before for several years, and I saw that here on the fair a lot is about vision, but in the sensor-based sorting there are a lot of other sensors which are needed to fulfill the needs of the sorting tasks, and I want to give an overview over those sensors and what the needs are for the future. First at all, not everybody knows about sorting technology in recycling, so I want to show you what's actually needed, which components are needed to sort some waste which is collected previously. So in general, we have an in-feed. Sorry. We have an in-feed for the material, we have a camera, we have a lightning. This is all probably common to other applications shown here on the fair. But additionally, for the sorting, you want to split the material stream into 2 or more parts. So we need additionally a valve to blow away some parts, that in the end we have an output fraction number 1 and output fraction number 2. And for sure the sensors are replaceable, but I will come later to various types of sensors. So the overall content of the presentation is that I show the functional principle a little bit more in detail, which I showed before. I will show some cameras and sensor techniques, and I will give examples of where the sorting is used. In which types of material streams, and I will give examples in which depths the material streams are separated. And in the end I will go over to what's coming next in sensor-based sorting technology. So first at all, how it works. Again, this is the same setup which I showed before, also with some visualization and some numbers. So we have the in-feed in number 1. This is needed to accelerate the material and transport it to the sensor where it's shown. Then we have the lightning source, we have the camera to capture the data, we have the computer to compute the algorithms to separate the pieces, to calculate which material it is, and to make the decision if it's going to be shooted by pneumatic valves or if it's pathing by. This is how such valves, for example, look like, and this is a row of valves. And in the end, at that position is where the sorting is happening. So the material is blown to box number B, or it's just passing by. And in this special application, which is shown here, is a shoot version. So the material speed in the position of the camera and in the position of the valves are around about 1 to 2 meters in velocity. At next, 2 different options are there to speed up the material and bring it in front of the sensor. It's on the left side a belt version, which is also commonly shown here on the fair, where the material is transported by a belt and the sensor is looking on the belt to identify the objects, or on the right side the shoot option, which was shown before already. There are different benefits for one or the other solution, but in general both are common in recycling industry. And so I want to go over to the sensors which are used. Here are some examples. First of all, the XRF sensor is capable of detecting the elements of a material what is falling beside or in front of the sensor. The resolution is not that high of XRF sensors because the technology is point technology and every single pixel is very expensive. But you have the benefit that you can see the element. You need for the lightning an X-ray tube, and you have the sensors to detect the X-ray fluorescence radiation of the material. Then another type of sensor is the XRT sensor. Another type of sensor is the XRT sensor. The XRT sensor is used to identifying the different densities of materials, but if you have a combination of two different types of sensors, you also can identify materials based on the elements, and therefore it's widely used, for example, in ore sorting. Then another type of sensors is the near-infrared sensor. Those are also partly shown here on the fair, and especially in the range of 1 to 1900 nanometers, you can see a lot of differences in which is used for ore sorting, plastic sorting, and so on. And not that common type is the lip sensor. Lip sensor is based of a source which is a sensor which is focused to a specific really narrow point. There you create a plasma on the surface of the material, and with the spectrometer you can get the signal, and also are able to calculate the amount of specific elements in the source which you are analyzing. Here's an overview over all the different sensors. You can see that all the sensors have different advantages and disadvantages. In general, you can say that the VIS or the UV inspection is the most cheapest and therefore the mostly used. But you have the other sensors, as I showed before, which are needed for specific applications, and therefore they are also used. So probably the common idea is that recycling, you do not need that advanced sensors, but the opposite is the case. We have so much to recycle, and there's so much value in the recycling material, especially when you have a purer and purer fraction, that even really expensive sensors are commonly used in various sorting applications all around in the first world. Mostly there's the money to sort in that cases, while in other parts of the world it's manually sorted. You can see, for example, that especially the XRT and the lip sensor and the XRF sensor are the most expensive, and to give you a feeling for how much the sorting machine costs, equipped with those sensors, it's between 500,000 and 1 million euros for just one single machine. So where it's used for, at first I want to show the example of glass sorting. When you think about the collection of glass in the glass boxes, you do not have only glass inside, but you also have metals, you have plastics, you have other material which shouldn't belong to the glass sorting, and everything has to be sorted out to get some pure fractions in the end. Some material that has to be removed definitely is the ceramics. They make problems later on in the recycling process, and you're using WIS sensors, UV sensors, XRF sensors, and near sensors for those applications. The purity which has to be achieved in the glass sorting is really high in the end. You need more than 99.8% of accuracy in the last stage of the sorting process. Also a problem is lead glass, which has to be removed, and those machines are not isolated as one machine, but it's a cascade of machines, and usually more than 20 machines are in one sorting plant, where the input is a mixed fraction and the output is shown here in the next slide. So the output is then the 3 or more different color fractions, which, as I showed before, has a purity of more than 99.8%. To give you an example for the metal sorting, the benefit of metal sorting is that metal has a high value, so there you can invest also more in the sorting technology. Therefore, in metal sorting, sorting technologies like XRF, XRT, and LIPS are used additionally to the VIS sorting. You have the heavy metals, which have the highest value. You want to sort out is the copper, zinc, gold, silver. But you also want to separate the light metals like aluminum or magnesium, for example. Stainless steel, you could also sort the stainless steel into subfraction of stainless steel. And so the e-waste is also coming together with the metal fractions and has a high value. You can also sort by shape, like this example on the right, for example, to sort out the coins of the metal fraction. Then another example is the plastic sorting. On the left side you can see the plastic, how it's collected, so before be shredded. Afterwards material is shredded and then sorted into the subfractions shown also in the row below. For the sorting of the plastics, you use a combination also of different sensors. Could be 3D, could be WIS, could be near-infrared, but also some specialties like mid-infrared or Raman, or again XRT or XRF, depending on the application. The purity which has to be achieved depends highly on where the material is going. So if you want to reuse it again, it needs a high purity, above 99%. If it's just going to reduce the amount of chlorine, for example, to give it to the incineration, then the purity doesn't have to be that high. Here's an example how such a sorter could look like. So this is a belt application. So you have to speed up the material on a belt. You're looking from with the sensors from above, and at the end of the belt there's the valve raw, and the decision is made to shoot the material into fraction A or fraction B. Some more applications I want to show, which are not that widely used, but there are some special applications, for example for wood, to separate wood into engineering wood, paper into subfractions like cardboard or high quality paper or newspaper. Then the municipal waste, which is a mixture of everything in the beginning and then goes into the subfractions. But also textiles, where we as the Research Institute AIT submitted a proposal to dig deeper into textile sorting in the last round of calls this autumn. The other sorting applications are also ore sorting, so not only recycling, but in the beginning, before the material is created, diamond sorting or industrial minerals. Therefore, you can use basically a variety of all different kinds of sensors, and it shows also in how much throughput you can achieve with different kinds of applications. For example, in the ore sorting, you can sort 100 tons per hour per meter of sorting width. What's next in the sorting process? On sensor side, it's going to be cheaper, more precise, and with high resolutions, as always. Then it's more common that niches are filled with some particular new sorting sensors which haven't been used before because they had been too expensive, for example, or they had been too scientific and not usable for the industry. They have to be really robust for sorting. The sorting machines, they are heading for new tasks, also using AI, like always in RGB sorting, but also AI based on all the other data streams we get from the other sensors. For the plants, they get be more automated as before, so always we had some hand sorting until now, but this hand sorting is going to be replaced in future by robots. The different sorting machines will be interconnected. On the sorting goals, especially for Europe, it's interesting because we do not have that much resources, so we want to close the loop, and therefore it's our interest in Europe to sort even more with more quality and to head for closed loops and to recycle material streams that can't be recycled until now. Here's one last example for the AI sorting, which is growing and growing really fast as everything is growing with AI. It's just using, in that particular case, the Viz, but you also can combine different sensors to get even more information and to build cheaper solutions where you earlier used high expensive sensors for different applications. Here's the list of the sources I have, and I want to thank you for your participation.